this specialized area. We hope that each session will be interactive, engaging, and insightful for all participants. To begin this workshop on an auspicious note, let us offer our prayers to Ma Saraswati, the goddess of wisdom and knowledge. We kindly request all the participants to stand in their place for this invocation.
Hi, Fraser. We'll start in just 2 minutes after the prayer.
Okay, no problem. Just let me know when you want me to start.
Yeah.
Thank you for joining the Vandana. Now I would like to invite Dr. Nandan Kumar, Sir, Director of HPT and ITT, to deliver the opening remark and share his thought on the significance of this workshop. Please welcome, sir.
Thank you, Shubham. Good afternoon, everyone. Today we have a unique combination of fiber manufacturer, researchers, and manufacturer of yarns. So without wasting time, let me introduce Mr. Fraser C. Thompson, who is going to be our first speaker. He's a sales manager for Shakespeare, and he's a highly experienced professional in the textile industry with an impressive 37 years dedicated to this field. Hailing from Perth, Scotland, Mr. Thompson began his journey with Bonar Yarns, part of Lowe and Bonar, where he held various roles over a span of 30 years. He then joined Dawn and Lowe, contributing significantly to the establishment of their graft extrusion business before moving to the Shakespeare monofilament. His expertise lies in extrusion-related manufacturing, serving the woven and tufted markets, including woven carpets, synthetic grass, and paper clothing machine. So, thank you so much, Fraser. Over to you. Please, you can share your screen and take it forward. Thank you.
Okay, thank you very much for the glowing introduction. You maybe have to help me with how to share the screen on this format because I haven't used it before.
We can share the screen, if.
Yes, if that would be very helpful. If you could do that, I'd be most grateful.
Just let me share.
So you are sharing or I?
You can just share from that.
Okay.
First up, thank you very much for the offer to attend and be part of this seminar, this workshop. I'm very grateful for the experience. If not slightly nervous about speaking in front of you all.
No, I mean, Fraser, it's about discussion session. I call it discussion session,
Okay.
where we all try to learn from each other,
Yeah. No, it's every day is a learning day.
Correct, yeah.
Will the screen visible?
So, I mean, you can see the screen, right?
Yes, I can see the screen. So if you move to the next screen,
Yeah.
Not this
Next one, yeah.
okay, I've got 17 slides. I promise I'll go through it relatively quickly. If I start to speed up in terms of my speech, please let me know and I'll slow down again. I can sometimes speak quite fast, but anyway, who am I? Well, there's the agenda. You can see what we've got to go through. So if we can just skip to the next slide, please.
Next slide.
So can you make a full screen mode?
I think this is the full screen mode, yeah.
No, this is not a full screen mode.
Okay, is it on full
Is
screen?
that visible now?
I don't think it is. Let me try one more time to see if I can get it on my screen. Right, okay, hang on a second. I might have worked it out. Let me know if you can see the screen.
I think we need to disconnect from here, then you can share your screen.
Okay.
Now you can just to give us a minute. Now you can share the screen.
I'm sharing it just now. Can you see? Can anybody see my screen?
Okay.
Not right now.
Okay, let me try one more time. Apologies for this.
So can I try it again? Slide.
Yes.
Okay, let me just share it again, sir.
Okay.
Now is it on full screen?
Yes.
Okay, thank you.
Okay. Yeah, so who am I? A very kind introduction there. As has already been stated, I've worked for 37 years in various roles within the extrusion industry, predominantly in the UK, but I've worked with companies overseas, India, for probably 25 years, give or take, in various guises. Next screen, please. Firstly, in fact, could you go to the next screen?
Next one, yeah.
Yes, please. So firstly, who are Shakespeare and what do we do? Well, Shakespeare is one of a series of companies that's owned by a company called Jadex. Jadex has a rough turnover of around $700 million a year. It has a big US base right across the USA. And we are a very good fit within that organization. We have our headquarters in South Carolina, Columbia. We have our conductive fiber plant in North Carolina, Enca, and the bottom picture there is the UK operation in the north of England. And if you could go back to the previous slide, please. So JDEX are owned by an equity house or a capital partner, if you want to call it that, called One Rock. Now, One Rock have probably 15 to 20 different companies that they own across the US. but we're all involved in the same kind of core business. So we're involved in petrochemicals, chemical-based, trimmer line, garden operations, film, food packaging. This is all the things that Shakespeare do. So we're a very good fit within the One Rock organization. Some people say it can be difficult to be owned by an equity house. It can be quite positive as well, because they're always keen to see you grow and invest in the latest technology. If we could move forward, please, on the next slide. And again. So Shakespeare in itself, in the UK and the US, we're involved in the extrusion of monofilament yarn, which is polyester, nylon, PPS, various other grades, polypropylene. We also make consumer products, so trimmer line, which is probably big business in the US and Europe. We are involved in the electronic antenna business. We make antennas in the US and the UK for military use and for commercial use. And we also in the US produce our own polymer, some of it for in-house use and some of it for external sale. Next slide, please. We also produce conductive fibers, which is where we are today. Shakespeare operates in the dissipative range. We are not conductive as such. We operate in a range of dissipative fibers between 10 to the 4, approximately, to 10 to the 8 or 10 to the 9. Next slide. So we basically produce two types of conductive fiber. We're involved polyamide nylon. So we extrude the nylon in the UK and we can ship it to our sister company in the US. They will then coat it. I'll come on more to that in a minute. But we operate in a fine denier range, which is 16 denier upwards to about 130. And we're involved in a heavy denier product for nylon, which is our Sandstart range, which is 400 plus denier upwards. We're involved multi-filaments. We can produce staple fibers, twisted yarns. We have a commissioned twister that we use in Europe, and they can produce a wide range of twisted nylon polyesters. And also within the polyester range, we have lightweight yarns, so 25 denier, 6 filament, 40 denier, 12 filament. Staple fibers, we operate within 3 DPF, 6 DPF. We're trialing a new product, an 8 DPF product. And again, twisted yarns through the commission twister. Next slide, please. In terms of the nylon products that we make, as I said, we extrude the yarn in the UK, we ship it to the US. They then have a unique suffusion process. This is a very kind of stable, high-end product that we're involved with. Polyesters, we do bicomponents. Fibers, we do multifilament. But both are involved at producing a high-end, high-tech product for the conductive fiber market. But we'll come on more into the end uses in the next slide, I think. So next slide, please. Thank you. So in terms of fine denier monofilament, these are the markets that we're involved with and that we bring competitive advantage to. Apparel, we have yarns that we use for clean room, workwear, industrial garments, even sports garments, sportswear. The 25/6 is woven into a fabric which is used for high-end sports applications to wick away static and reduce the static buildup in sports. In fabrics, we are involved with industrial filtration, upholstery, intelligent textiles, and also in the carpet, where the conductive fiber can be used either air entangled or twisted into the carpet pile yarn. So these are all general markets that we're involved with, and markets or sectors where it's important to have a dissipative yarn If you're working in clean room or anywhere where there's petrochemical or static buildup, and I think this will become more, well, this will be a bigger market coming into the Indian, or this is a growing market within the Indian sector, I would have said, but I'll come on to that at the end. Next slide, please. In terms of heavy denier monofilament, PMC, this is what we call the paper machine clothing market, which is a big industry within India, especially between Calcutta, Delhi. There's some big companies you have in India that produce this material. And this is basically where the yarn is woven into a very large fabric. And that fabric is then used to press paper and form paper. The anti-static yarn is, in some instances, used within that fabric to help the process and help dissipate any static buildup, which could negatively impact in the production of paper. This, by the way, I see some people writing some notes, which is very kind, but you feel free to circulate this presentation to anybody who wants it. In terms of staple fiber, that's we have yarns that we cut to specific lengths. Again, we use a commission company for that. But that staple fiber is also used in conveyor belts to wick away static, filtration fabrics, dry filtration, anti-static brushes. It's also used in carpet production. One of the companies or one of the business units that I used to be involved with makes a product called Flotex, which is very high-end carpet, and the anti-static fiber goes into there, and it's predominantly used in hospitals, that carpet. In terms of polyester yarns, again, 5 main markets: barrier fabrics, which involves clean room, medical, pharmaceutical; liner fabrics, which is military; medical fabrics, which garments, the curtains, the table covers, and again, even the carpet area, I would consider a medical fabric because it has to have the same anti-static requirements. We have protective clothing, so flame retardant workwear for the fire and rescue service. These are all areas where the conductive fiber ends up. So it plays a key part in many aspects of production and people's safety. And I'm talking generically here. Conductive fibers play a very key role in maintaining safety and maintaining product efficiency or production efficiency. Next slide, please. So these are just some of the basic range of products that we do. I'm not intending to dwell on this. So we do a basic, most common product here is RO22. That's probably our mainstay. But the last 3 products on the right are very popular within India for lattice apron production. So we have a lot of companies that we work with within India, which is good because India is a country that I love to visit. So it's always a good excuse when you're there to give yourself a reason to return. Next slide. And again, these are just some of the nylon 666 products that we produce, both in staple form, which I've mentioned previously, that goes into conveyor belts or filtration or to the carpet business. Next slide. And these are some of the twisted products. We use a commission twister in Europe. This is a very small selection of what they can do. But again, it goes into speciality, high-end juice. Product here is woven into a fabric and downstream into other areas. Next slide, please. These are some of the polyester products. Again, polyester staple fibers. Some of the fine denier products that we do, the 25/6, which goes into sportswear, and some of the other products as well. Some of it, we've actually found a new market, a new application, which I guess is relevant, and that it goes into protective shoe wear. So we now have a fiber that goes into protective shoe wear. Next slide. So one of the points on the agenda, if you noticed it, was how long have we been in India? Well, we work very closely with our valued partner, Mr. Ninad Joshi. And he has been with us as a company for 25 years. He has a huge range of knowledge within all aspects of the textile world, having spent all of his life in it. One of the good points about traveling around India is I get to experience the food, and I make no apology for the photograph. This is in one of your hotel chain restaurants. So where it can be a bit messy and we're forced to wear these garments. But Ninad's been with us for 25 years. He is our man on the ground in India. He not only represents us, he helps us, he guides us. And for a long time, we've been developing the business within India. So the next slide, please. That's a very quick whistle-stop tour of what we're involved with in terms of the conductive fiber market. But one question which I would be very keen to understand is on the next slide. If you could move forward, yeah. And is how do you, as a consortium, if you like, see the market evolving? Because I think there's some exciting times within the Indian market. There's a lot of movement of businesses from one geographic location coming into India, I think. I think India has positioned itself really well in this marketplace in terms of the technology available, in terms of the labor skills, and in terms of government help and companies setting up business there. So I would very much like to hear, as well as any questions, where you think your market is going. Thank you very much. I appreciate that was a very fast tour, but I hate to bore people early on in the afternoon.
Thank you, Feather. I'll answer your question, but before that, I just want to ask a very simple question. You have mentioned that the new product is being developed for protective shoe wear. So
Yes.
how is that different from what we are using right now for twisting with cotton or Modaclake or Aramid? How is that different from current products?
This is a spun fiber, a staple fiber that's going in. And if I'm absolutely honest, it's one that just came on the horizon 2-3 weeks ago. So we're still very much in the developmental stage with it.
Right.
But yeah, it's an interesting market. You think of protective cleanwear in terms of outer garments, in terms of hats, in terms of gloves, anywhere, the petrochemical or the telephone industry where you're making you need clean room areas. Shoes is never something I'd actually considered. And this, in part, is the inside of the shoe and not necessarily the outside. So yeah, it seems a very, very small niche market, but every day is a school day, as they say, you learn.
No, that's true. That's true. I mean, let me just get a few questions. If there's any question from anyone in the audience, if anyone wants to ask any question.
Yeah, thank you, sir. Am I audible?
Yeah,
Yes.
Please go ahead. Yeah, please go ahead.
Yeah, I have been talking with the AIMS people and IIT people. You have rightly said that clean room is where the demands is going to come, because semiconductor industry, medical industry, and which requires really clean room. And can you elaborate more, how that is made? What is the market scenario in other countries? What kind of the products? Because clean room, I have seen that there is a certain people who are saying that we want to develop clean room because we want to set up labs, R&D labs.
There's many facets to the I believe, and I am 6 years new to this market, so my knowledge is not as good as some of the people here, obviously, on the call. But clean room environments, you've probably seen. I think when I first started coming to India, there was a large growth in the number of car manufacturers coming into India. I think Pune was one of the main ones. Volkswagen, Volvo, I think, set up there 15 years ago. Now, these areas all need clean room. where you're involved with paint, dust, anti-static, it's all clean room. Telephone production, the mobile telephone production. I think that's growing within India. That's all clean room environment. So it's not just labs. There's a multitude of different areas, gas, petrochemical. And I think India has positioned itself, if I've understood your question, apologies if I haven't, I think there's huge potential within India, and there's growth coming into India within these markets, and that will see a large increase in demand for conductive fiber, I believe. I'm not sure if that answered your question. Please let me know.
No, my question is that, like, where your fiber, how it is used, like, do you have any case study where you have developed some product? So that we can get some inspiration on that area. Like, ultimately we can import, but how we can make it with using your conductive fibers?
Yeah.
You're right. I will cover that in my presentation when I'm going to talk about how we are manufacturing the yarns using Fraser's anti-static staple fibers as well as filaments. Like, I have got some samples. They have just developed a white color as well, which is very interesting. So I mean, we will cover that in that session.
Okay.
If there's any more question from Fraser, else I need to answer his question of Indian scenario.
So just one question.
Yeah, please.
I mean, as far as the testing of workwear is concerned, we have to follow certain standard like EN 1149 part 1, 3, 2, like that. So for protective shoes that you are telling us, like we have developed this kind of shoes which is having anti-static property. So which sort of standard we have to follow right now?
Well, we're further down the food chain than that, and it's not our product that has to be tested. It's the finished product that has to be tested. So I will defer to the people who are at the front end of the production process or the supply chain. They will know which standards they have to meet. But you're right, there's a lot of specific standards that have to be met globally on these products.
But we are facing this because we are facing this problem right now. Few of the shoe upper manufacturers, they have designed a very good shoe upper using our yarns, and they can only do surface testing. They can't do charge decay because the sample is not enough to fit on the machine. So I mean, maybe we need to talk to ISO or something. There must be something for shoe, especially the charge decay type of test.
Yeah, I normally we would defer. If we have a query on something, we would defer to one of the independent test houses. You have BTTG, Shirley, and there's one in Scotland. There's 3 in the UK that I know of. There's bound to be some within Europe as well, and India. So liaise with these companies, liaise with the independent test houses, and they will help you develop a test or develop one for you.
Yeah. Is there any more question?
What about conveyor belt testing?
Again, I would say that's the same kind of. It's the end producer, the customer who makes the final product has to test his product. I grew up with flame retardant yarns where we supplied flame retardant polypropylene into the carpet industry for aircraft carpets, and it's not up to us to test the individual components. It was up to the carpet manufacturer to test the end product. So again, same answer as before, to be fair.
Thank you. Thank you.
I have one quick question. Most of the time we are using your 40 denier and for twisting. So I believe you have also 24 denier available in this.
Yeah, 25/6. So it's a finer product, but yes, we have that available as well.
So is that available? Is that available in Indian market as well, or is
yes.
restricted in Europe?
No, it's not restricted. Yes, you can buy. Certainly, and that's a conversation we can take offline if you want to have a conversation with Ninad and myself. Then yes, there's nothing off limits.
We'll discuss some of the challenges we are facing in our manufacturing. When we use this, I'll discuss that in my slide. Okay, great. If there's any more question, otherwise we'll move on to our next session where we have highly renowned researchers like to share their views. So any more question?
Thank you very much for your time. It's much appreciated.
Thanks, Fraser. So for next session, we have um, Dr. Suraj and Dr. Satish. Are you here? I think Suraj is here, right? Right. Okay. So I'll introduce both Dr. Suraj and Dr. Satish. We are working together from last maybe 3 years now on developing some unique electroconductive yarns. So brief introduction about Dr. Suraj. He received his PhD in electronics and electrical engineering from the University of Leeds in 2008. He then worked as a postdoc research associate at Leeds University until 2011, focusing on quantum cascade lasers and high mobility devices. Subsequently, he moved to Northwestern University, USA, as a research fellow, where he researched dilute magnetic semiconductors. In 2012, Dr. Khanna joined CSIR NPL in New Delhi, India, as a principal scientist. Since July 2017, he has been serving as a senior principal scientist. His current research interests include large area memristor devices based on e-textiles, which are suitable for biomimicking and have the potential to function as synaptic devices with integrate and fire behavior similar to biological neurons. Dr. Khanna has co-authored over 100 SCI journal articles over the past 16 years, including several published in the Nature publication work, Advanced Optical Materials, and Applied Physics Letters. So we have Dr. Khanna, and you want me to introduce Dr. Satish as well, so both of you can help us, right? So Dr.
Yeah,
Satish is a distinguished researcher in the field of biomedical engineering. He earned his PhD from the Indian Institute of Technology, Delhi, in 2020, and holds an MSc in electronics and MTech in microwave electronics from the University of Delhi, completed in 2003 and 2005, respectively. Dr. Satish has been serving as a scientist at the Electrical and Electronic Metrology Division of CSIR, National Physical Laboratory in New Delhi. He's there since 2009. His research expertise spans DC and impedance metrology, material metrology, instrumentation control, biosensors, e-textiles, RF and microwave technologies, and measurement automation. So I really like to say thanks to both of you for helping us out in textiles. This is a very new area for all of us. So over to you guys.
Yeah, thank you, Dr. Nandan, for elaborate and it's a great opportunity for us to discuss and talk about our findings and the exciting work which we have been doing from past 3 to 4 years. Okay, so if you may allow, like we have few slides to go through, like,
Yes,
and
please.
then probably that will create a number of questions in the audience, and then probably we can take the discussion ahead after that.
Yes, please.
So I'll just try to share my screen. Entire screen. Video allow. PPT. So I hope you can see this.
Yeah, it's coming, I think. Yes.
So it's full screen now.
Yes, sir.
Yeah.
Okay. So basically what we have is like we started around 3 years ago with this electron yarn basically. So what we want to share is like the yarn is already in production in last, I think, probably uh, how many, 15, 20 years? And mostly the
Yes.
testing which the industry was doing for this was anti-static testing, what do you call, set protocols. Okay. And when we had the opportunity to work with Dr. Nandan, like because we are based out of a Metrology Institute of India, so we always had a liking to look at the things in a more detailed way. Okay. So we started testing these materials in a more what do you call detailed protocol which we use at our place. Okay.
Just a minute, yeah. So this is one of the we have presented in University of Delhi, so you can show their logo.
Yeah. So our apologies for that. Like we 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 happen to use the same slides, but but I hope it'll convey the full message. Okay. So what we found was that if we tend to test the materials, which is basically electroconductive yarn and fiber, so that can show a very unusual kind of properties which are not usually seen or were expected to be seen in these materials. Okay. So what we did was we managed to what do you call publish three very good papers out of it. So first one is where we have shown a typical a memristor kind of behavior. I'll come to that, like what is it, and then we had shown the same behavior first in the yarn and in the textile, and then we had shown the synaptic device kind of behavior in the yarn also in our third papers. And then in the fourth paper, we had developed a memristor kit, which can be used as a what do you call a teaching apparatus in schools and colleges. Okay, and we'll try to cover the what applications we have in mind for these materials also. Okay, so this is where we are based at. This is our what do you call the main campus, which is based out of Delhi, and it's a pretty old campus. As you can see, that foundation stone was laid around 1947, and we have been functioning from 1950. Okay, and basically what we do broadly at NPL is basically we try to provide the metallurgical traceability for all the 7 basic SI units. Okay, so we provide this kind of traceability to all the different industries and manufacturing facilities out of India. And why we need metallurgical traceability, like that is basically the essential requirement for the quality management systems for calibration laboratories, and then it can help us maintain accuracy, and then it helps in standardization of measurements. Okay, and all these things are required when we are talking in terms of international trade. Okay, so that's the core responsibility of NPL. Why is it not going to the next slide? Hello, are you there?
Yeah, we can hear you. Yeah, we can hear you.
Okay. Okay.
Yes.
So we are based at this division 2 at NPL, which is electrical and electronics metrology. Okay. And okay, so what is the problem and the need? Okay. So what basically is required is smarter, body compatible, wearable electronics kind of materials, which has given rise to electronic textiles. Okay. And these electronic textiles, what they do is they provide electronic functionalities into the wearable clothes which we put on, and thus it has what do you call brought upon a new kind of terminology which is called as wearable technology. Okay, and this is a kind of what do you call speculation. What we have is like uh, already 2024 is gone, so the market has already reached around 54.2 billion USD for this wearable electronics, and we expect it to grow towards around 200 billions by the end of 2034. So there's an immense what do you call scope of growth in terms of these new materials and their different applications. Okay, so just to give a glimpse, like we found like few product launches which happened in January 2023. So these are the few companies like which are listed over here, and they've tried to cater to healthcare and what do you call heated textiles and displays. Okay, and there are a range of other companies also which are based across the world and which are trying to bring about many different new applications which could be based on these conductive textiles. So what you have to understand is like now the world is trying to move away, or maybe it is trying to diversify in terms of finding new and new applications in terms of conductive textiles. Now it's no longer restricted to just anti-static applications. Okay, so that is the key information you have to take away, that conductive textile does not mean only anti-static applications. Okay, so there are a range of applications which are coming up. I hope that point is clear to all of you.
Yeah, that's correct. Yeah.
Okay, so this is the material which we began with. Like we were fortunate to find Dr. Nandan, and then he was as an expert, like he has been making these HPT yarns, and typically it has 80-20 ratio of PET metal fiber, what do you call filaments, or you can say fibers. Okay, and the same yarn can be knit into e-textile. Okay, so now what happens is like with traditional knowledge, if people try to measure the resistance of this yarn, it would turn out to be highly resistive. Okay, and people would consider it to be a insulator. Okay, using any multimeter if you happen to test any length of this yarn. Okay, but when we use a special kind of equipment which we have got here, with which you can change the what do you call applied voltage across the yarn. So then what you would see is like initially your yarn could be in a high resistive state, and then it could go to a low resistive state as you change the as you apply a high voltage across it. Okay, so that was a very key uh, behavior which we discovered rather. So, so I think somebody is desperate to reach me over the phone. So I would ask Dr. Satish to please carry on in next few slides. I'll just attend my phone call. Just give me some time.
Okay, so over to the next slide. Okay, so we are fortunate here in NPL belongs to a group, electrical and electronics metallurgy, where we are looking after resistance, capacitance, and inductance. And fortunately, we discovered we discovered the memristive properties in this yarn. So that also belongs to the, this is the fourth circuit element. So we are fortunate enough. So we were able to discover that, and it's a unique finding. Till now, nobody has looked that yarn in that perspective. So this is, if we will go to the background of the memristor, so it's theoretically in 1971, Professor Chua from University of California, he has theoretically proved that there could be a memristor element which is missing, and it is known as the fourth circuit element, the fourth electrical circuit element. And then after so many years, in 2008, this the first demonstration came into the picture from the HP lab, where they have demonstrated a 3 nanometer memristor, which is as an experimental device. So you can see this is the experimental device, and this is the first memristor that came after more than 2 decades. So these are the okay. So after we have discovered that memristor properties, so we have looked over the application. There are so many applications nowadays. If you can see, the entire rigid electronics is moving towards the flexible and wearable electronics. So the entire electronics, whatever available in the market at present, which is rigid PCB based. So nowadays, everything is moving towards wearable and flexible electronics so that it can have the variety of applications. So okay, so this is the material that we have used for our findings. So this is one of the PET fibers. It's a composite material from PET and stainless steel fibers, and merged together it is. Uh, um, Dr. Nandan is fabricating those composite yarns. So those yarns has the unique properties. Like if you can see, this is the yarn, and these are the since these yarn can't have the rigid contact, so we have initially used these soft contact. So these are the soft pressure contact. This is the one electrode, this is the second electrode where the contacts are forming, and this is our DUT, device under test. So that we have measured, and since this is in the textile form, it has a isotropy. So in one direction it has a better you can say better connectivity, so it will have a less resistance, and in high resistance in waves direction, and in coarse direction it's a low resistance, slightly lower, but still in the high resistive state. So and these all fibers are non-continuous in nature, as you can see from this electrode 1 to electrode 2. So if we will apply, okay, this is the SEM data. So you can see the composition of stainless steel and PET fibers across the in the data. So the bright spots are stainless steel, and the darker spots are PET fibers. So we have measured this. So we have utilized the source meter, which can excite or sweep the voltage across the DUT, and simultaneously we are measuring the current. So we can calculate the resistance properties, and this is the simple apparatus we have used. And to record the data, we have used the automation so that we can have a large number of data set to plot the IV curves. And initially we were surprised that we were only getting, every time we are exciting, we are measuring the resistance, at each time it's a different resistance. So initially we were thinking that it's a linear, the properties could be linear, but later on we have discovered that the properties are non-linear, and that's why we are facing the initial hurdles. And when we have plotted this IV curve like this is the DUT we have, and okay, this is the first paper in which we have discovered, okay, how the memristic properties will look like. Initially, these are reworm properties. Like worm is a special kind of uh, non-volatile memory, which says write once, read many. So it's a non-volatile category of memory. So in the first paper, what we have reported, so since this is the semi-log plot, this is the current in the logarithmic log axis, and this is the applied voltage. So as you can see, at the initially it is high resistive state, you can have a um, you can say the current is around in the femtoampere range, and when it clears some threshold voltage, it starts accumulating the heat, and due to the joule heating, it jumps to a sudden jump to a this is the conductive state. So since this is the logarithmic scale, that's why we are looking at a butterfly. So this is the ohmic or the conductive state once it is switching from high resistive state to the low resistive state.
And I think this is one of the most important thing which you have to take away, that this material is not a typical material which can be handled in a very, what do you call, a typical standard protocol. Because if it happens that the material gets excited by a higher voltage, it can suddenly turn into a conductive material. Okay, so that you have to understand that if you are using or working with this material, it can show two different states. First state can be highly insulating and other state can be highly conductive. So depending on what excitation voltage you are using, it can show two different behaviors. I hope that is very clear to everyone.
Yeah, that's fine. Yeah, correct. Even
Because
I'd like to add to that, we have made a new yarn for you where we are using Shakespeare's filament in core and the staple fiber on
Mhm.
sheet. So that will be interesting. You have two types of material in the same yarn. So that will be,
Perfect.
something will
We
keep
would
you
love
busy for 6 months,
to. Yes, we would love to have a, what do you call, play with that material. Okay. So I would state again to all the audience, like, it's generally it is pretty okay to go with the conservative way of testing the material, but at the same time you have to be very careful to understand your material fully. Okay, because that is very important, because you may not intend your material to be conductive in some particular application which you may be wanting, but if it happens to be excited by the correct voltage, it can turn into conductive. Okay, so that's the main takeaway from this finding. And okay, you should ask us that why this is happening. And so the basic reason for this is, like, PET is generally insulating, but then it can respond to joule heating. Hello,
Yeah, please go ahead.
there was some echo behind it. So this PET typically a phase change material which can go from being less crystalline to more crystalline as you apply joule heating to it. So basically, what is happening is, in the initial part of the IV, where the material is acting like highly insulating. So at that period or at that time, the current or the low value of current which is able to pass through the material, it is creating lot of material. So as the joule heating is happening, your material of PET. PET is basically uh, transitioning from less crystalline to being more crystalline. Okay. So as that is happening, your current will increase across the material. Okay. And as the current will increase, it will go to a memory switching state, and it'll then behave like a standard ohmic material which would be having few, maybe 80 to 100 ohms of resistance. Okay, so basically it changes from giga ohms of resistance here to few hundreds of ohms of resistance here, by only applying a nominal voltage of how much, 2 to 3 volts. Okay, so I hope that is absolutely clear to you.
Yep, fantastic. Yeah.
So this is some what do you call more scientific input which we can look at. Like we can use the same data plotted in a different way, and then we can try to find out what kind of conduction mechanisms are happening across the same device at different voltages. Okay. So initially it shows thermionic emission, then it goes into SCLC, trap filled SCLC, and then finally it goes into ohmic conduction. So so we may not have more time to go through this graph, but you're welcome. Means you can go through the paper and then you can come back to us if you have further queries. Okay. So this gives the historical evidence that some other groups in the past also they have tried to work with the with PET, not in the yarn form, but in the thin film where they've grown a thin film of PET in between two gold electrodes, and they have also seen that as the field across the electrodes is increasing, you can see a sharp increase in the current across the PET. Okay, so that basically supports our finding. Okay, so here what we have is we have more than one cycles of the device being run, and every time it shows the similar kind of behavior where it goes from a highly resistive state to a ohmic state. Okay, so now we move to a fabric. So the same yarn, when knitted into a fabric, it shows typically similar kind of behavior, which was seen for the yarn. Okay, but here we found one more thing that when instead of applying directly voltage, if you're applying current, so then you can see multiple states between the highest high resistive and low resistive state. Okay, so these are the additional states which we were able to record or visualize because we were now applying current. Okay, so we were able to control. We were able to apply the current in a very fine controlled manner. Okay, so that's why we were able to see more states in between the the first and the last resistance state of the device. Okay, so that basically summarizes that if you are applying 1 milliamp, so the device may read something around 700 ohms, and then if you increase it to uh, 2 milliamp, the resistance falls, and then so on and so forth. Like if you go to 10 milliamp, the device resistance may go down to roughly 200 ohms. Okay. So as you're applying a higher current, the resistance falls. So because now the material is in a fabric form, and this fabric is known to have high anisotropy, so that's what we saw uh, in the device testing also. So when the device was tested in the coarse direction, we saw that there is a more uniform what do you call spread of heating. So basically what is happening here is we are applying current only across this blue color DUT3, and we were trying to understand that if we are applying heat just here, so how much it can extend in this direction. Okay, so all these DUT 5, 6, 7, 8, they were measured, they were only measured, okay, along this direction. So what we see that 4 and 5 basically closely follow the behavior of the active DUT, which is DUT3. So as the right current is increasing, the resistance is falling, okay, for these three devices, okay. But as you move beyond DUT5, so there is almost no change in the resistance state of these three DUTs. Okay. So that was happening in the coarse direction. Now, when we talk about the wale direction, so there is almost no spread in the wale direction. So if DUT3 is this, DUT9, 10, 11, so there was almost no heat spreading in this direction. We had only heat spreading in the coarse direction. Okay, so that was a very unique finding which we had, and we can summarize it in this diagram, where this is our active device and the heat is spreading because it's a continuous medium. So that's why it is obvious the heat can spread, but it was spreading only majoritarily in the coarse direction. There was no heat spreading in the wale direction. So we found that a similar kind of behavior happens in the neuron. Okay, so when it is trying to send signal from this its soma to its tail, so then in the middle, the transparent long bar, that is a low resistance path, and the yellow ones are outside the high resistance path. Okay, so these high resistance areas, they are helping to confine your signal which is originating from the head and going towards tail. It is confining it within the axon. Okay, so the middle part is axon, and similarly the textile can be operated by putting more than one active duties, and a low resistance path can be created in the middle. Okay, and across there could be a high resistive path. So this was a very unique thing which we proposed, where we said that the material can be operated in a way where it can biomimic the communication happening in a neuron. Okay, so we had biomimicked one behavior of the neuron, and then we said, okay, in the neuron, there is another phenomena which is happening, which is called integrate and fire. So basically, what happens is each of the neuron is connected with hundreds of other neurons, which provide one small iota of signal to the head. Okay, and this head basically integrates all the small signals coming, and then once that integrated value goes beyond a threshold, so then the head fires in the sense it sends out a signal. So we were able to show the exact same behavior in the yarn. Okay, so here you can see where we have resistance in the x-axis, in the y-axis, and the time on the x-axis. So all these circles, what you're seeing are the small signals which are coming to the head of the nerve cell, and it is integrating. Okay, it is integrating all these small signals, and then once it reaches to a threshold, the resistance falls. So basically fires, and then again it starts integrating, and then once it goes to a beyond a threshold value, it again fires. Okay, so that's how we were able to show that our yarn can also biomimic the integrate and fire phenomena which is being seen in nerve cell. Okay, so here also it integrated all the signals arriving to it, and then in one go it changed from a highly resistive to a low resistive state. Okay, and how it was happening was, like, here we were using a transcranial magnetic spectroscopy system, which is basically a 8-shaped coil, which onto which we apply thousands of volt of supply, and that creates what you call time varying magnetic pulses. Okay, so those magnetic pulses, they basically what do you call
Induces.
yeah, it basically in it interacts. Okay, so here this technique is basically used to reignite the dead neurons in any patient. Okay, so basically the idea is, before applying it to the patient, the technique can be further optimized using our active material, Where is the photograph? Okay. So our active material is basically on the other side of this white bar. Okay. So that white bar can be used to calibrate and optimize the dosage of this biomedical technique before actually applying to the patient. So I hope that is clear. And now we move
That's
on
great.
to
Yes.
like we managed to make a small demonstration kit out of it, so which can be used as a tool for the user, where they want to, if they want to see that which are the two different states of resistance the material can have, and how they can be operated. So basically, in our laboratory, initially we used maybe 10-15 lakh equipment. So we to apply bias to the material, but then we replaced it with a small what do you call 6 volt battery. Okay. So with the 6 volt battery also, it is doing the same thing. If you remember, I said that if you apply the correct required voltage, so you can switch the material from a high resistive state to a low resistive state. So that's what we managed to show using what do you call handheld batteries and a small simple multimeter. Okay, so initially the resistance was around 22 kilo ohms, and then once you use the battery, it falls to 340 ohms. And then this was subsequently published in one of the science magazines. And then these are our few what do you call visits where we had gone to demonstrate the behavior of our material. And okay, in conclusion, like we can say that we were the first one to find these two states in the what do you call electroconductive yarn and textiles. And then okay, we have shown biomimicking, we have shown integrated fire, and we have also shown a memristor kit. And we are already in on the way to submit a patent also, where we have claimed a few more applications using this material. So it's all looking very exciting. Like we have many more ideas to work on and to chase a few new proof of concepts. Okay, so ultimately, like down a few years from now, like what we are expecting is that our research will lead to means it will contribute to both aspects, like one more towards wearable technology also, where new applications would be shown, that what new material, or in terms of wearable technology, what new can be done. And on the other side, we are also focusing on the biomimicking kind of thing, like by using this very, very cost effective material, what new in terms of material with memory and biomimicking behavior, what new applications we can develop. So we are trying to target both aspects, like of the current requirement. Okay, so with that, I think we have covered most of the things which we wanted to say, and these are our email IDs. And of course, like you can get back to us if you have any questions or queries. And also, we can have some more discussion as of now. And lastly, like these are few of our collaborators with which we are undertaking our work. Of course, HPT is on the top here. Many thanks to Dr. Nandan for his continuous support and motivation. Okay, so I think we would like to close the session with this. And okay, I'll quote Dr. Vikram Sarabhai: "He who can listen to the music in the midst of the noise can achieve great things." Okay, so I'll hand over the floor to Dr. Nandan. So if we have more things to discuss, we can continue.
And before closing the session,
Thank
I
you.
would
Thank you,
like to
Dr.
emphasize
Suraj.
that this is the novel memristor kit that we have developed, and there is no you can say no kit available for the students to have the demonstration how the memristor works. So this is, I think, globally the first memristor kit, which is very cost effective, and it can be utilized by the university and the schools to understand how memristor works. That's why most of the students doesn't know about this memristor, because there is no experimental kit available to them in the academics. So that's the unique point of this memristor kit. Thank you very much.
Great, great. Thanks, Dr. Suraj, Dr. Satish. Maybe, HPT has to sponsor 100 of these kits for schools in Panipat and Sonipat, So we need to discuss,
Yeah, we should. I think that will give a lot of what do you call visibility to our
to
work.
students, yeah.
Yeah,
Yeah,
and maybe yeah,
yeah.
please tell you.
Coming back to our textile application, we have, India may host Olympics in 2036 or 2040. So there are a lot of funding available for sports textiles. We are also doing a lot of work on sports textiles. So, can you think of some application where we can scale up this development, or we can optimize this yarn? Just to give you idea, right now I gave you 20 gram per 1,000 meter yarn. Okay, we can make 10 gram per 1,000 meter. Okay, we can make it very fine yarn. But just we need to think of how we can bring this to sports textiles, or because we are going to see a massive uh, business coming up in India related to sports textiles because of push from government, because of Olympic, and so just something for you to think and help us out.
Yeah, I think we may need to spend some time and have few more discussions to bring
Yeah.
about something new in this area.
If there's any question from anyone, please feel free to ask Dr. Suraj or Satish. Otherwise, we'll start the next session where I'd like to share my views on manufacturing issues,
Sir, I
which
have
we
a
are.
question.
Yeah, please.
Good afternoon, sir. Sir, my question is, for some other applications, can I weave these electric yarns, since you have told us about knitting of the yarns? So can I make woven yarns? And since woven yarns we can't stretch, so what will be the changing of properties from knitting to weaving, aspects of resistivity or resistance?
But from my side, I can tell you, Sachi, yes, you can weave. All we can do, we can give you 2-plied yarn. So that will be easy for you for weaving. For Dr. Suraj, we have given them single ply because they wanted to knit it. And once you have done woven fabric, then probably NPL team can help you in characterizing. And Dr. Suraj, Dr. Satish, you want to add something to this?
No, I think you have appropriately suggested, like once the material is fabricated for what particular application Sachi may have in mind, so then we can step in at that, help in characterizing it in a fullest of the way possible.
Yeah, basic unit is yarn. So whatever you made out of the yarn, it will amplify or some addition to the, if you made the fabric out of that, either knitting or weaving, it will add to the properties or some deviation to the properties, not huge deviations. So the basic unit is yarn. Whether you use it in fabric or knitted fabric or the woven fabric, it's just a geometry.
Okay, okay,
So
sir. Thank you,
broadly
sir.
speaking, Sachi, if you are going to use the same yarn which we have reported, so then the broad behavior will remain the same. That the material will show two states. Initial state could be insulating, and then as you apply a higher voltage or a higher current to it, it may switch to a low resistance state. Okay. So that property will be there.
Thank you.
Okay, so it will not like stretching, as you said, the veil direction and pose direction. There is slight difference, but in woven fabric, we have what we have warp and web, so it will not affect that much, right?
No, the basic behavior will still remain the same. But the thing is, if
Students
you are
will
going
do.
to,
Yeah.
yeah, the basic
No,
behavior will remain the same. And I think more in uh, the fabrication, like probably Dr. Nandan can help. Like he can suggest. Like
Yeah,
I
because of
can
the
tell you from.
geometry of that. Yeah, because of the geometry of that fabric or the isotropy in the fabric, it will show the properties. Some addition or some deviation in the properties, minor deviation, not much.
And let me tell you from my experience what we have seen. Most of the time when we are testing our material, we are washing it 5 times to up to 50 times based on client requirement. Okay. That's where your major difference will come when you are talking about knitted or woven, because in knitted twist is less. So what we are saying that because of less twist, these fibers may come out more quickly than the woven fabric, because in woven fabric you have more twist. Okay, so that's for the reason we want to conduct this workshop. So if any students would like to take this as a project, we can help you with raw material and we can look into woven versus knitted, because twist will be high in woven samples. Because of high twist, you have stainless steel fibers more twisted together, and probably after multiple washing, losses will be less. So I mean, hope that gives you some idea which direction we can do a proper research, in this field.
So, one
Okay,
more
sir. Thank
question.
you.
Yeah. Yeah, please go ahead.
Sir, actually, is there any criteria for a particular product that it should have this much resistance? Then we can say it is insulative or conductive. For example, when we are testing our sample, the surface resistance for any conductive sample should be less than 2.5 into 10 to the power 9 ohm. So that is the criteria for any fabric to pass. But when we are talking about yarn or some other things, is there any certain criteria through which we can say it shows the conductive behavior or the insulative behavior?
I think some of the times it is application based, but there is some generic terms like if we divide the whole range into insulating, conducting, and then one of the dissipative. So there are three category in which we can divide the entire range of the conductivity or the resistivity of any of the material. So that's how we can on the application on. So for different application, it can have a different criteria to say if you are treating it as a interconnect or if you are treating in a system, it has to have a very high conductivity. But for certain application, you can relax.
Thank you. That's I
Yeah, please.
Sir, you have mentioned in slide 5 and 6, I think so. Sir, why PET fiber goes from less crystalline to more crystalline when you apply Joule 80? Because we know by increasing the temperature of the material, that will tend to decrease the free volume in the material, and material have more direction of flowing and orientation will increase. So from this phenomena, material should be less crystalline. So why is it happening? PET is going from less crystalline to more crystalline after applying Joule.
because it passes through its glass transition temperature. So when the glass transition temperature approaches, so basically you can have more structured domains. Okay, so that's why your crystallinity increases, and it's a very well-known phenomena for phase change materials. Where as you move transition temperature, So the overall crystallinity of the material that increases.
Thank you, sir.
Okay, sir, in your experiment, you have applied a very less voltage. I mean, from 1 volt to you goes up to 4 volt. What if we apply 100 volt or 200 volt, something like that, that is much higher than you have used in your experiment? So what will happen at
Yarn
that
will
time?
the pet will burn. The pet will burn. It will go beyond its melting temperature also. Melting temperature is roughly, I think, 300 something, 383 or something is the melting temperature. So once it goes beyond its melting temperature, it goes, उसका breakdown हो जाता है. It breaks down basically. It gets burnt.
And we have controlled it using the compliance current. So once you are keeping the very limited current, it won't burn. But if the current goes higher to a level, then it will burn, because this is ultimately current has to convert into the joule heating. So it's I square R.
Great. Great.
Okay.
Thanks so much. I'll share your presentation and IDs to everyone, and so they can continue discussion later if they want. So what I will do, I will share my slides, and I just want to share our manufacturing issues and some few ideas about testing, and obviously need help from both manufacturer and researchers to correct us if we are doing something wrong. Right. So about myself, I'm the director of High Performance Textiles Private Limited, where we are manufacturing these types of yarn under our brand name HPT Antistatic. And most of the time we are using staple fiber as well as filament to manufacture these yarns. So just to give you idea, this type of raw materials, this is in the fiber form. So when we are using these type of fiber, we need to blend it with other materials, and we pass it through blow room carding, draw frame, speed frame, ring frame to make yarn. On the other side, sometimes clients they need grid form in the fabric. Just to give you, I don't know if this is visible. This type of fabric, if you see it closely, you'll see a black grid every 10 centimeter in both warp and weft direction. That can be achieved by twisting these filaments, which is 40 denier, twisting these with modically cotton, aramid, or any types of yarn, and then use it at the time of weaving. So two types of raw materials are available. One is staple fiber, other is filament, and then we have these are stainless steel base material. Here we are talking about 8 micron to 12 micron. So this is also used for filter applications, for applications which is not used for protective textiles, because most of the time I have seen complaints from end users about the irritation because of stainless steel fiber. So most of the time this is used for applications where it's not coming next to skin. So this is also, we do draw frame blending and speed frame, ring frame. So yeah, I mean, manufacturing these materials are, it takes time to understand the issues, and because these are costly materials, it's time for us to understand what are the challenges. Like Dr. Suraj rightly said, that we need to know what we are producing, or we need to know what we are buying from overseas. So a very brief introduction, what is anti-static as well as static dissipative. There are a lot of communication gap, I will say, is happening. Many times people, they think that anti-static means static charge won't be there. The material won't let static charge to be generated. It's not the case. The idea is we need to dissipate the charges which are being generated. So why it happens? The simple Reason is friction, contact, separation of materials leading to charge accumulation, any relative motion or physical separation of materials which leads to electrostatic charge generation. And once again, idea is how to dissipate or how to let it discharge without stopping any accident. And obviously, right now, what's happening most of the time, we see that these accidents are not classed into this category. So in case if this something happens in operation theater, that will be reported as a fire in the operation theater. We are not getting the reason why this fire happened, why sudden explosion happened in the factory. So that is the concerning part, that right now we are not talking about categorizing our hazards based on these issues, or slowly it's coming there. So most of the times clients are asking about these materials just because it's mentioned in the specification, not because it's actually needed. And obviously, there are few ways where we can reduce these type of accidents. Grounding is one of the way. Most of the time factories are grounded properly, machines are earthed so that the charge accumulation should not happen. Humidification plays important role. We have done our own testing where we are seeing variation in results when we are keeping RH at 20% up to 50%. There's a lot of variation in result. So RH plays a very important role. Again, coming back to protective textiles, which is the core of our interest. Like I said, fibers are available. We can convert fibers into yarn. Yarns can be converted into fabric, woven fabric, knitted fabric. Non-wovens are manufactured using these fibers, and obviously garments are being manufactured. So from manufacturer point of view, what I've seen so far, there are 4 ways yarns are being manufactured in India, maybe in overseas also. First, the easy option is twisting. You take this 40 denier or 24 denier, and you take 2 more yarns or 1 more yarn, and we have a simple 2-for-1 twisting machine, TFO, and you twist it together. Now there's a lot of challenge if you do like that, because you have all 3 yarns together, and it will depend how good you have made the package, and then you are twisting it in the TFO. So we have done that, and we saw many problems when you have a yarn manufactured using TFO, and we don't recommend manufacturing these filaments using TFO technique, because if you just do a case study where you try to manufacture 500 kg and you just check your wastage, the wastage level will be very high if you are using TFO technique. Then you have twisting with core, where these filaments are fed in core, and then twisting is happening on surface, on the top of it. That means the core is just inside, and then materials are on top. So there is no twist in the core. So your core is completely untouched. And the third one is ring spinning, where you are blending the staple fibers. And obviously, fourth one is the most interesting one, where you have staple fibers blended in the fibers. At the same time, you have these materials running in the core. So you are doing core spinning of a yarn where you have staple antistatic fiber as well as filament antistatic fiber. Yes, the percentage goes very high. The price will go very high. But these are the innovations happening globally. And there are a lot of interesting development happening in this field. So the key part is, how do we know what you are buying is the correct product? That is the most concerning issue for a manufacturer like us. We really need to work closely with our suppliers, like we are doing. We are working very closely with Shakespeare, where we try to develop products and keeping the raw material same, so that we get good support on the raw material side. So again, with the help of NPL and Dr. Sundar and Dr. Satish, we are still working on how we can make testing of these materials very simple, so that you import say 200 kg and 300 kg and you send one cone to NPL, and NPL can help you test with the raw material and you get a certificate. So you have a peace of mind that your lot which you have bought is correct without producing the yarn. That should be the case. We should be able to test our material before we are able to use it. So again, just one or two slides before we discuss more about this various issues we are facing. So 1149 is the most commonly used standard for testing of products manufactured using these materials. So it becomes very interesting because whatever yarn we are making, I mean, again, with Dr. Sudha and Dr. Satish, we are working on how to test these yarns in a consistent way. But right now, as per standard, we need to make a fabric before we test the properties. And again, woven fabric, knitted fabric, non-wovens, any form of fabric we need to make. So 1149 is having 5 parts. Part 1 talks about surface resistivity. We will have demonstration after this session. We will show to students who are here. So this is very common. Most of the labs in India, they have this surface resistivity test method available in their lab. The important part is we should be asking these labs what is the RH they have maintained while performing this test. Because this is where the report varies, because one lab is doing test at 40% RH, second lab is doing at 20% RH, and there's a difference in result if your RH is different. And that's important that, we should ask for the RH used and temperature used. The second one is vertical resistance. That means testing through the material. The first is surface. The second is testing through the material, surface resistance, where you are not only checking the resistance of surface, but you are also checking, across the material. That's known as vertical resistance. The third one is most important one, I feel, the measurement of charge decay. Because what happens, both your surface as well as vertical resistance, this can only work with your materials such as stainless steel or surface conductive materials, where you have fibers having carbon or graphene on surface. The moment you are using core conductive material, where the conductive material is hidden inside core, your surface resistance can never tell you whether the material is antistatic or not. So that's where we need to use charge decay test, where you are not touching the material, you are just checking the antistatic properties with the help of electrode and a voltage checking appliance. We'll show that in the next slides. So charge decay is most important because here it doesn't matter if you are using core conductive or surface conductive fiber, the results will come and that result will be valid globally. Garment test, I think this is under preparation. This standard is not ready right now, but I'm sure sooner or later you will see a special testing method just for garments. Fifth one is performance requirements. So part 1 is most commonly used for workwear, which is the core of our business. This is also included in EN 420, which is used for gloves. And now for gloves, we have a separate standard EN 16350, which is based on 1149 part 2. Here the requirement is 1 into 10 to the power 8 ohms. And this is the 2 examples I have tried to show here. On one side, you can have a fabric where you can see this is the fabric here. The fibers are blended across the yarn. So you cannot see any grid form. It's intimate blend, and you just see the black stripes slightly. And the black stripes coming because the anti-static fibers is in black color. And other situation is where you have grid form. So you see the filaments in the grid form. And both samples needs to be tested as per 1149 part 1 and 1149 part 3. And this is a simple basic principle how 1149 part 1 is being tested. But like I said, we are working with NPL on calibrating our machine or working together so that we do it correctly. based on their guidance. And for textiles, one thing is very important. If your samples are not disposable garment, if you are not using a disposable garment, the samples must be washed 5 times to 50 times before testing. This is something I'm seeing a lot of cheating happening. We have a lot of certificates where samples are not washed and it's just tested and says that, oh, it passes the test. But what happens when you wash it 5 times or 10 times or 50 times? Because most of these work wears will be used and washed multiple times before it's being discarded. Part 2, like I said, it's tested across the material. Basically, we are trying to check the resistance across the material, through a material. Probes are different. We will showcase in our demonstration how the probes are different. Here also, pre-treatment is important. And for those companies who are into protective textiles, this is also a part of ISO 11611, where vertical resistance to a material should be greater than 10 to the power 5 ohm. Charge decay test. We are playing with this kit from last 2-3 months, and we have learned a lot. And the principle is very simple. We have a voltage generator. We can go up to 1200 volts. And without sample, we are checking the maximum electric field. And once you put the sample, then you are checking the electric field. And basically, we are, let me just show. Yeah. So maximum electric field is measured without sample. And then we are putting sample and we are checking the reduction in electric field. In case your sample is conductive, charge will be induced. And that's the reduction of electric field is being measured. And, so half decay time is reported and shielding factor is reported. So half decay time is 50% of the charge should be dissipated in less than 4 seconds. So this is a small video where we tried to use with a normal polymer sheet just to show you. So bottom we have a voltage generator. So before we put the sample, we are checking the charges available. So we have to make sure that we are using ionized gun to remove all charges before testing. So initially electric field was generated and then we put the sample and then again we are checking the reduction in electric field. Like I said, RH is very important. So the whole area RH should be 20% to get a good consistent result, which can give you same results as that of European labs or overseas labs. So we have maximum electric field and then reduction because of the polymer material. So, like I said, this is a very interesting area, and this cannot be solved by one company or one organization. We really need to work. We really need to get help from experts and suppliers so that we actually should know whatever we are doing is correct or not, or how we can improve this. So if there's any question or any suggestion, please feel free. I think now what we'll do, we'll conclude this session, and we have shared our email ID. Please feel free to reach to us if you are interested in doing any project or any more development. We are open for all ideas, and we'll have our demonstration session now, but that will be offline because we need to do that in our lab. So thank you so much. Your comments are welcome.
Thank you very much.
Thank you, Professor. Thank you.
So
Thank
before
you.
Proceeding further, we would like to have a group.
Can we just take one group photograph?
Yeah.
Yeah.
Yes.
Just a group photograph. Thank you. Yeah. Sure, you can take the.
Yeah. It's recorded, so it will be.
Great. Thank you so much. Have a nice day and keep smiling.
Thank you.
Thank you all for joining.